So try to picture this for me. You're a new third-year medical student starting your first clerkship, which happens to be internal medicine. So your team has been called down to the ER to admit a patient to the general medicine floor. And after you see the patient, your resident hands you what looks like a little receipt on which there are various numerical values. And then she asks you, "So, what do you think is going on with this patient?" Well, this exact scenario happened to me, and I'm pretty sure it'll happen to you. And so, best to be better off than I was in that situation and be prepared to interpret this little receipt, which is actually an arterial blood gas, or an ABG, and is supposed to give you some insight into the acid-base status of your patient. That is, if you know how to interpret it. So an ABG gives you a lot of information to work with, including, but not limited to, the pH, the partial pressure of carbon dioxide, or PCO2, the partial pressure of oxygen, or PO2, and the bicarb ion concentration. And for reference, the normal values for pH are 7.35 to 7.45. For PCO2, it's 35 to 45 millimeters of mercury. For PO2, it's 80 to 100 millimeters of mercury. And for bicarb, it's 22 to 26 milliequivalents per liter. Alright, so there are a few different systematic ways of interpreting blood gases, and the steps that I'll give you here are just my preferred method. I think the real key is to be systematic about it. In other words, find a method that you like and stick with it. So the first step is to look at the pH. Basically, you have to determine if the patient is acidotic or alkalotic. So this is easy enough. If it's below 7.35, then the patient has some sort of acidosis, and if it's above 7.45, then they have some sort of alkalosis. So now let's say they have some sort of acidosis. The pH is on the lower end of normal. The next step is to look at the PCO2, or the partial pressure of carbon dioxide. And this is to determine if the acidosis is due to respiratory acidosis or metabolic acidosis. If the PCO2 is higher than normal, then they have a primary respiratory acidosis. In other words, their acidosis is due to a buildup of carbon dioxide in their blood. If the PCO2 is lower than normal, though, then the acidosis can't be explained by increased carbon dioxide in the blood. It is therefore a primary metabolic acidosis. Now, with metabolic acidosis, there are two additional calculations that need to be carried out. The first calculation is the anion gap, which is the difference between relevant cations, so in this case sodium, and the relevant anions, which are chloride and bicarb. And I'll just make a little bit of room here. So a normal anion gap would be somewhere between 8 to 12. And if the anion gap is normal, there is one set of differential diagnoses to consider. If the anion gap is increased, however, then there is another set of differential diagnoses to consider, and the mnemonic used for that differential is mud piles, which stands for methanol, uremia, diabetic ketoacidosis, paraldehyde or fenformin, iron tablets, lactic acidosis, ethylene glycol, and salicylates. So remember this mnemonic, mud piles, for any sort of increased anion gap metabolic acidosis. The second calculation used in metabolic acidosis is called Winter's formula, which is used to calculate the respiratory compensation and to check if this compensatory response is adequate. And Winter's formula is just 1.5 times bicarb plus 8, and then there's sort of a fudge factor of plus or minus 2. And then that is supposed to give you your expected PCO2. So once you calculate the expected PCO2, you compare this to the actual PCO2 given in your ABG. If the actual PCO2 is higher, then you know that there is a concurrent primary respiratory acidosis. And if the actual PCO2 is less than the calculated or the expected, then you know that there is a concurrent primary respiratory alkalosis. And if you think about it, this kind of makes sense. If the PCO2 is higher than the expected compensation, then the patient is not breathing off enough carbon dioxide. So there is a respiratory acidosis. And it helps to recall that carbon dioxide is an acidic entity. And the same thing for if the actual PCO2 is lower than the expected or calculated PCO2 for a respiratory response. If the patient is breathing off too much carbon dioxide, then they will have a concurrent respiratory alkalosis. All right, so that's it for acidosis. Now let's talk about alkalosis. So just as with acidosis, the next step is to look at the partial pressure of carbon dioxide. The same thing goes for alkalotic patients. So if the partial pressure of carbon dioxide is decreased, then we know that our patient has a primary respiratory alkalosis. So in other words, the alkalosis can be explained by the fact that there is decreased carbon dioxide in the blood. If partial pressure of carbon dioxide is increased, though, then the alkalosis can't be due to the increased carbon dioxide. We know instead that there's a primary metabolic alkalosis. And each of these has their own differential diagnosis set associated with it.